All right, in today's lecture, we're going to cover the first part of the section 5.6 material on the ratio test. So this is another test that we will learn for convergence or divergence of series, which is usually applied if the general term of our series involves a factorial or constants being raised to the nth power. So let's look at what this test says. Here, this next theorem is the ratio test for series. And it says if we have a series, say the sum from n equals 1 to infinity of some general term a sub n, and the limit as n approaches infinity of the absolute value of the ratio of successive terms, that is, the term a sub n plus 1 divided by a sub n is equal to some number L. Then we have three possible results for this ratio test. The first is if the limiting value L of this ratio is less than 1, the series is absolutely convergent. If the limiting value L is greater than 1, the series is divergent. And our last case, if the number L is exactly equal to 1, we say the test fails. In this case, we have no conclusion that we can make about convergence or divergence of this series. So what this ratio test, or the way it works sort of intuitively, is if we look at the ratio of these successive terms, that is a sub n plus 1 to a sub n, if that ratio is greater than 1 for large values of n, that means that the numerator is growing more rapidly than the denominator for large values of n. So that is the next term in our sequence, the an plus 1 term, is larger than the term before it. So we're going to start adding terms of larger magnitude, and we would see divergence in that case. But as long as this limiting value is less than 1, that means our successive terms are getting smaller as n gets larger, and we would expect to see convergence. So that's sort of the intuitive idea behind this ratio test. So let's look at some examples where we would make use of the ratio test. I mentioned that we typically want to use this test if the general term of our series involves a factorial, or if we have constants being raised to powers of n. So in this first example, where we have like this -3 to the nth or 5 to the n plus 1, that should immediately make me think of the ratio test here. So in our first example, let's see how this ratio test works. To apply it, we're supposed to look at the limiting value as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. So in this example, we have the limit as n approaches infinity of the absolute value of, our numerator is a sub n plus 1. So that's what we get when we take this general term of our series and replace all of the n's by n plus 1's. So here we would have -3 to the n plus 1 power divided by n plus 1 times 5 to the n plus 2 power. And then we're supposed to divide by a sub n. That is the general term of our series. Now, in almost all of these examples that we consider, the general term of our series, this a sub n term, is a fraction. So when we divide by a fraction, that's the same as multiplying by its reciprocal, or multiplying by the reciprocal of the denominator. So rather than dividing by a sub n, equivalently, we can multiply by the reciprocal of a sub n. So here our numerator would be n times 5 to the n plus 1 power. And then we're dividing by -3 to the nth. So here, if we go ahead and rewrite this as multiplication by the reciprocal of the denominator, it saves us a little bit of work with writing out the steps of these problems. Now, once we write out the expression for this ratio, we'll see that in a lot of these problems, these terms in the numerator and denominator can cancel or simplify. So let's see what's going to cancel here. In the numerator, we have a -3 to the n plus 1 power, and in the denominator, we have -3 to the nth. So we can cancel n factors of -3 on top and bottom. We're left with -3 to the first power in the numerator. Now similarly, in the numerator, we have 5 to the n plus 1 power. In the denominator, we have 5 to the n plus 2. So if I cancel n plus 1 factors of 5 on top and bottom, that leaves me with 5 to the first power in my denominator. And then our last terms that we have are n and n plus 1, which don't cancel directly here. So let's write out what we're left with. We now have the limit as n approaches infinity of the absolute value of, well, in our numerator, we had one factor of -3 left over times this n term. And then we were dividing by, in the denominator, we had one factor of 5 left over. We were multiplying by n plus 1. So after simplifying a little bit, let's see what we have. We've got the limit as n approaches infinity of, now taking the absolute value of our numerator, -3n, we have +3n, and then we're dividing by 5n plus 5 if we distribute the 5 through the denominator. And what we're left with is the infinite limit of a rational function where we have the same highest power of n on top and bottom. So recall that for these infinite limits of rational functions, where we have the same highest power, the limiting value is the ratio of those lead coefficients for the highest powers of n. In this case, 3/5. Now, this limiting value that we find for the ratio is less than 1. Therefore, the ratio test says that our series is absolutely convergent. So here we could say the series converges absolutely by the ratio test. So here our conclusion was that the series converges. Moreover, it converges absolutely, we know, by this ratio test. So let's look at some other examples to see how this ratio test will work. In part B, we have the sum from 1 to infinity of n to the 10th times -5 to the n divided by n factorial. So in this example, as soon as I see that factorial term, that should immediately make me think of the ratio test. Anytime that you have a factorial in the general term for your series, the first test that you want to apply is the ratio test. And we'll see why the ratio test works nicely with these factorial terms as we move through this example. So in general, to apply the ratio test, we're supposed to look at the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. So here a n plus 1 over a sub n. So in this example, we have the limit as n approaches infinity of the absolute value of. So for a n plus 1, we have n plus 1 to the 10th power times negative 5 to the n plus 1 all over n plus 1 factorial. And then we divide by a sub n, but again, since a sub n is a fraction here, this general term, rather than dividing by this fraction, we could multiply by its reciprocal, which would give us n factorial divided by n to the 10th power times negative 5 to the nth power. And again, we're going to see what we can simplify, which terms can be simplified by comparing our numerator and denominator. So in this example, we have in our numerator negative 5 to the n plus 1 divided by negative 5 to the nth. So we can cancel n factors of that negative 5 on top and bottom, and we're left with negative 5 to the first in our numerator. Our n plus 1 to the 10th divided by n to the 10th. Well, those terms don't cancel or are reduced nicely. And this last part that we're left with is n factorial divided by n plus 1 factorial. And I claim that this is just 1 over n plus 1 after simplifying. Now, to see why that's the case, let's look at this ratio. If we're looking at n factorial over n plus 1 factorial, let's think about how this could be simplified. If we think about how a factorial is defined, our numerator, n factorial, is defined as the product of n with every integer value less than n through the number 1. So that is n times the integer 1 less than n times the integer 2 less than n, and so on, until we get down to the integers 2 times 1. So if we're then dividing by n plus 1 factorial, well, based off the definition of the factorial, we would have n plus 1 times the integer value 1 less than that, which would be n, times n minus 1, n minus 2, and so on, until we get to 2 times 1. So looking at which of these terms cancel, well, we see a factor of n cancels, n minus 1, n minus 2, and so on, so that the only term that we're left with is a division by n plus 1. So this n factorial over n plus 1 factorial leaves us with just a factor of n plus 1 in the denominator. So let's write out what we have here. We've now got the limit as n approaches infinity of, in our numerator, we had n plus 1 to the 10th power times 1 power of negative 5. Then our n factorial divided by n plus 1 factorial gave us 1 factor of n plus 1 in the denominator times this n to the 10th power. So here we see we could simplify a bit further. We have an n plus 1 to the 10th divided by n plus 1 to the 1st. So that leaves us with n plus 1 to the 9th in our numerator. So here we have n plus 1 to the 9th power times negative 5 over n to the 10th power. Or taking the absolute value of this expression, we have the limit as n approaches infinity of 5 times n plus 1 to the 9th divided by n to the 10th power. So here we have the infinite limit of a rational function, the quotient of two polynomials, and we see that if we were to expand our numerator The highest power that we would have is n to the 9th power. And then our denominator involves n to the 10th power. So we have a higher power in the denominator. So as n becomes infinitely large, our denominator is growing more rapidly than the numerator. So we have a limiting value of 0 here, which is less than 1. So the series converges absolutely by the ratio test, since this limiting value was less than 1. So here we can say the series converges absolutely by the ratio test. So we see in this example, part B, why we would want to use the ratio test when the general term of our series involves these factorials. When we take a quotient of terms involving factorials, they usually simplify quite nicely. So let's look at some other ones. In this next example, we have the sum from 1 to infinity of n plus 1 times 2 to the nth over n times 3 to the 2n power. So for simplicity's sake, here I might rewrite this 3 to the 2n power as 3 squared and then raised to the nth power. So here we would have the sum from 1 to infinity of n plus 1 times 2 to the nth divided by n times 3 squared, or 9, raised to the nth power. So for this general term of my series, as soon as I see these constants being raised to the nth power, say 2 to the nth or 9 to the nth, I should immediately think of the ratio test. Anytime we've got these constants being raised to nth powers or factorials, that suggests that we might want to try this test. Now the way that the ratio test works is that we look at the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. So in this example, a sub n plus 1 would give us n plus 2 times 2 to the n plus 1 power divided by n plus 1 times 9 to the n plus 1 power. And then we divide by a sub n, but again, since a sub n is a fraction, that's the same as multiplying by the reciprocal of a sub n, which would have a numerator of n times 9 to the nth power divided by n plus 1 times 2 to the nth power. So let's see which terms will cancel here, or which can be simplified. So starting with the factors of 2, we have 2 to the n plus 1 over 2 to the n. So canceling n factors of 2, we're left with 2 to the first in the numerator. Then we have the constant 9 to the nth over 9 to the n plus 1. So canceling n factors of 9, we have 9 to the first on bottom. And then these other terms involving polynomials of n don't simplify directly here. So let's see what we're left with. We have the limit as n approaches infinity of the absolute value of, for our numerator, we're left with a constant 2 times n plus 2 times n. And in the denominator, we were left with a constant of 9 times n plus 1 times n plus 1. So here we have n plus 1 squared. So taking the absolute value through the numerator and denominator, well, since n is positive, both our numerator and denominator are always positive. So distributing the expression in our numerator, we have 2n squared plus 4 times n And in the denominator, if we expand, we have 9n squared plus 18n plus 9. So at this stage, we have an infinite limit of a rational function where we have the same highest power of n on top and bottom, n squared. So the limiting value is then the ratio of the lead coefficients for those highest powers of n. In this example, 2 over 9, which is a number less than 1. So if this limiting value is less than 1, we know by the ratio test the series converges absolutely. By the ratio test. All right. So in our first few examples, we were seeing convergence of these series, or absolute convergence, guaranteed by the ratio test. Let's look at another one. In part D, we have the sum from 1 to infinity of 2n plus 1 factorial over n factorial. So here immediately, as soon as I see those factorial expressions, I should think, let's try the ratio test. So here, the first step for the ratio test is to look at the limiting value as n approaches infinity of the absolute value of an plus 1 over an. So here we have the limit as n approaches infinity of the absolute value of. So let's think about our an plus 1 term. Here, if I replace n with n plus 1 in my numerator, let's see what we have. Here I'm going to be a little more thorough in showing my work to explain what happens with this numerator term, the 2n plus 1 factorial. So if I replace n by n plus 1, I would have 2 times, not just n, but 2 times n plus 1, and then plus 1 factorial over my denominator is then n plus 1 factorial. Then we divide by a sub n, but again, since a sub n is a fraction, this is the same as multiplying by the reciprocal of that fraction, which would be n factorial divided by 2n plus 1 factorial. So let's see what we have here. This is the limit as n approaches infinity of the absolute value of. So let's look at this first expression that we have in square brackets here. If I distribute that 2, I have 2n plus 3 factorial. So we have 2n plus 2 plus 1 gives me that plus 3 factorial, divided by, or times, n factorial, also in the numerator, and then the whole thing is divided by n plus 1 factorial times 2n plus 1 factorial. So let's see what we can simplify here. So we saw from our earlier example that the ratio of n factorial divided by n plus 1 factorial leaves us just an n plus 1 in the denominator. So let's start there. We have the limit as n approaches infinity of the absolute value of. In our denominator, we know that we're going to have a factor of n plus 1. Now let's look at these other factorial terms. We have 2n plus 3 factorial times 2n plus 1 factorial. So if we were to write out those general terms, or the product of all the factors for 2n plus 3 and 2n plus 1 factorial, well, we see in our numerator, we would be left with the term 2n plus 3, and the next integer less than that would be 2n plus 2. Now, the next term after that, 2n plus 1, and the product of all of the other integer values less than that, down to 1, would be exactly 2n plus 1 factorial. So all of those remaining terms, 2n plus 1, 2n minus 1, and so on, cancel, and we are left with just those two factors, 2n plus 3 and 2n plus 2 in the numerator. So here, taking the absolute value, well, since n is positive, both our numerator and denominator are always positive, so we are left with 2n plus 3 times 2n plus 2 over n plus 1. So to simplify here, there's a few ways that we could go about this. One thing I could do is from this term, 2n plus 2 in the numerator, I can factor out a 2, and I'm left with 2n plus 3 times n plus 1, if I factor out a 2 from that 2n plus 2 expression. And then I'm dividing by n plus 1, so I can now cancel a factor of n plus 1 in the numerator and denominator, and we're left with the limit as n approaches infinity of 2 times 2n plus 3. So as n gets large, this quantity grows without bound. We have a limit which does not exist. So here, this limiting value is certainly a value greater than 1. So in this example, we can say the series diverges by the ratio test. So in this example, we had divergence of our series. So in our next example, let's consider trying to approximate the sum of a convergent series. So this example is sort of similar to a problem that we had looked at a little bit earlier. We have the sum from 1 to infinity of n plus 1 times negative 5 to the nth over n times 3 to the 2n power. So here, as I did in my earlier example, this 3 to the 2n power, I may rewrite a little bit as 9 to the nth power. That is 3 squared and then raised to the nth. So here we have n plus 1 times negative 5 to the nth all over n times 9, or 3 squared to the nth. So we're simplifying this just a little bit. And because we have these constant terms being raised to powers of n, that should make me think of the ratio test. So in part A of this example, we are asked to prove that this series converges absolutely. So to do that, we could apply the ratio test, which says we look at the limit as n approaches infinity of the absolute value of a sub n plus 1. So here our numerator would be n plus 2 times negative 5 to the n plus 1 divided by n plus 1 times 9 to the n plus 1 power. And then we divide by a sub n. But again, a sub n is a fraction, so rather than dividing by that fraction, we can equivalently multiply by its reciprocal, which would be n times 9 to the nth power divided by n plus 1 times negative 5 to the nth power. So let's see what we can simplify here. So we have negative 5 to the n plus 1 divided by negative 5 to the nth. So canceling n powers, we're left with negative 5 to the first as our numerator. We have the constant 9 to the nth over 9 to the n plus 1. So canceling n factors of 9, we're left with 9 to the first in our denominator. And then all of the other terms are polynomials in terms of n, which don't simplify directly. So let's look at what we're left with. We have the limit as n approaches infinity of the absolute value of, for our numerator, we had a leftover constant of -5, and then we had an n times n plus 2, also in the numerator. And then we were dividing by, in the denominator, we have a constant of 9 to the first, times n plus 1 times n plus 1, which would give us n plus 1 squared. So taking the absolute value through our numerator and denominator, we have for our numerator a positive 5, and if we distribute the 5 times n, we have 5n squared plus 10n. And then expanding through the n plus 1 squared in our denominator and distributing the 9, we have 9n squared plus 18n plus 9. So we're left with the infinite limit of a rational function where we have the same highest power of n, that is n squared on top and bottom. So our limiting value is then the ratio of those lead coefficients. So in this example, 5/9, which is less than 1. So we're guaranteed that this series converges absolutely by the ratio test. So here, for part A, we are guaranteed this series converges absolutely by the ratio test. So that's what we wanted to prove in part A. So we know that this series is converging. That is, it's approaching some fixed sum S, but we don't know how to find the sum of an infinite series unless it is a geometric series, or if it's telescoping, where we can find an expression for the nth partial sum. But for this series, it is neither geometric nor telescoping. So if we can't find the actual value of the sum of this series, we might try to approximate it. So in part B, we are told to use S3, that is the third partial sum, to approximate the sum of our series and estimate the error in that approximation. So let's start by finding the third partial sum, S3. That is the sum of the first 3 terms of our series. So here let's maybe rewrite this general term from the previous page. So we have the sum from 1 to infinity of, it was n plus 1 times -5 to the nth over n times 9 to the nth power. So starting with the first term of our series, if we substitute 1 in for n, we have 2 times -5 to the first divided by 1 times 9 to the first. Then we would add our next term. So plugging in 2 for n, we have 3 times -5 squared over 2 times 9 squared. And then plus, for the third term, we have 4 times -5 cubed over 3 times 9 cubed. So here, the sum of the first 3 terms of our series would be the following. With the use of a calculator, something we could simplify this if we wanted to get it down to a single fraction. But here, we could just leave it in the following form. So this sum of the first 3 terms is an approximation for the sum of the series. And then we're asked to approximate the error, estimate the error in that approximation. So to estimate the error, we need to think about what type of series we have. And in this example, we have an alternating series. This negative 5 to the nth power, well, we see that for each value of n, or each subsequent value of n, we have an alternating sign, or a sign that's differing from the previous term. So for alternating series, we had a theorem known as the remainder estimate for alternating series. So let's recall what that says. By the remainder estimate for alternating series, the error in the nth partial sum approximation, which would be the absolute value of R3 here, since we were using S3, the third partial sum, to approximate the sum, is bounded above by A4. That is, in general, the absolute value of R sub n is less than or equal to A sub n plus 1. So here, let's look at the fourth term for that series. Substituting 4 into our general expression for the series, we would have 5 times 5 to the fourth power divided by 4 times 9 to the fourth. So that is 5 to the fifth power over 4 times 9 to the fourth, which reduces to 3,125 over 26,244. So this expression is the maximum value that we would have for the error in our approximation. So that is the largest that or the furthest off that this third partial sum is from the true value of the sum of this series. So in the last part of this example, we're told, well, what if we needed to approximate the sum of this series to accuracy within 1 decimal place? So to get accuracy to within 1 decimal, we would need the error in our approximation to be less than 0.1 or 1/10. So let's see how many terms we would need to add to get that accuracy. By the remainder estimate, for the alternating series test, we know that the error in an nth partial sum approximation is the absolute value of the remainder, R sub n, which is less than or equal to the n plus 1 term of our series. So here, that n plus 1 term is given by n plus 2 times 5 to the n plus 1 power divided by n plus 1 times 9 to the n plus 1 power. And we know that to achieve the desired accuracy, we want this maximum error to be less than 1/10. So here we could try to solve for n, but we can see pretty quickly here that it's not going to be so easy to solve for n explicitly. In fact, here it's impossible to solve for n explicitly. So we would need to start testing integer values of n to see what the smallest value of n is that would achieve this inequality, or that would make this inequality true. So here, by testing values of n, we find that n has to be at least 4. So if n is greater than or equal to 4, the inequality holds. And we have the desired accuracy. So in order to approximate the sum of our series, we would need to use the fourth partial sum or higher, more terms. So here, S4 is the sum of the first 4 terms of our series. So again, the sum of the first 3 terms we found in part B. The first term was 2 times negative 5 to the first divided by 9 to the first. Plus we had 3 times negative 5 squared divided by 2 times 9 squared. Plus our next term is 4 times negative 5 cubed over 3 times 9 cubed. And then for our fourth term, we would have 5 times negative 5 to the fourth over 4 times 9 to the fourth. So this sum of the first 4 terms of our series would give us accuracy for the true value of the sum to within 1 decimal place.